So up until now, as we've talked about uniform circular motion, the one question that we've sort of neglected is, why is it that an object chooses to follow a circular path? And the answer is that there has to be something that holds the object on that circular path. And the label we give to what it is that holds that object and keeps it going in a circle is the centripetal force. We know forces are vectored. Just like any vector, we can think about its magnitude and its direction. So for the magnitude of the centripetal force, I can calculate the magnitude of the centripetal force by taking mass times the centripetal acceleration. So the centripetal acceleration is v squared over r, so speed squared divided by the radius of the circle. So the magnitude of the centripetal force is simply going to be mass times v squared over r. In terms of direction, as I look at this equation, if the centripetal force is equal to mass times the centripetal acceleration, since mass is always positive, that tells me that the centripetal force and the centripetal acceleration have to point in the same direction. So if I know that the centripetal acceleration always points towards the center of the circle, then that means I know that the centripetal force always has to point towards the center of the circle. The reason objects follow a circular path is because there's a centripetal force that acts to hold them on that path. Now, to be clear, this is not a new force. Okay, so we're not adding some new force to the set of forces that we've already laid out. If we think about Newton's second law tells us that the net force equals to mass times the acceleration. And what we've just said is, well, the centripetal force is equal to the mass times the acceleration when an object moves in a circle. What this means is that the centripetal force is not a new force. It's simply a name for the net force that acts on an object to keep it moving in a circle. Okay? So when you have uniform circular motion, you'll still have the same set of forces that can potentially act on an object that we've been talking about so far this semester. It's their net force that gives you the centripetal force. One of the things that we want to make sure when we're working our Newton's second law problem, we're still going to draw the forces we've been drawing in the free body diagram. Gravitational force, normal force, friction force, tension force, a spring force if we needed, applied forces. Those forces are still going to be in the free body diagram. The centripetal force is not a force that we draw into the free body diagram because it doesn't go on the sum of the forces side of the equation. It is the MA side of the equation. The way Newton's second law works for a uniform circular motion problem is that it basically says that the sum of the forces acting on the object, so the sum of these forces that act on an object, equals the centripetal force. Whatever these forces, whichever ones of these forces are acting on your object as it moves in a circle at a constant speed, it's the vector sum of them that is equal to the centripetal force. So we're not going to draw the centripetal force in our free body diagram because, again, it's not a new one, right? It's simply a name that we give to the net force when an object undergoes uniform circular motion.